And we're recording. Cool. Welcome everybody to lab. So today we're going to be covering fast adders. And I'm going to take you a little bit through the theory just as a refresher. You should have already gone through most of this in class. But just so that we have it as a reminder. Yeah, that's the one. All right. So these are the slides from the lecture. Hopefully you've seen these before. They're not new. If not, you can grab them in the files on Canvas. But basically, we start with a fast adder with the realization that our current implementation is suboptimal, and the reason it's suboptimal is because every stage has to wait for the next stage. So every stage has to wait for the previous stage to finish. So if I'm just going to follow this through. Basically, there's my Y and my X, and if it comes through, blah blah blah, whatever. This stage 1 can't do anything until it knows whether or not it's going to get a carry bit, right? So no summation can be performed here until we know whether or not we're going to get this carry. And we don't know until this stage 0 has done its thing. That may not seem like a big deal when you've got a 4-bit adder. It really isn't. But when you're doing a 64-bit multiplier and you're trying to do that 10 million times a second, this stuff starts to become a big deal. And so that's why we need more efficient adders. All right. So, to realizing basically that this carry is the culprit, we can come up with a generic expression for our carry chain, and we realize that for any CI plus 1, this GI plus PGI minus 1 plus PI minus 1 CI minus 1 is our equation. That sounds a little confusing. We first have to realize what our GI, PI, etc. are. So GI is X1 or XI, YI, and PI is XI or YI. And that will make sense as you start to look at the circuit here and realize, what are we actually asking? We're asking this stage here, we'll call CI plus 1, relative to this CI here, is asking basically, okay, did you have an X and a Y? That's the first question. Did you have an X and a Y? That's this G value here. Let me pull that up in a different color. Set that to red. Okay, so the previous stage wants to know, or the next stage wants to know if the previous stage had both X and Y. If it did, then we know immediately that it's going to carry out because it has 2 1s, right? It can only ever have 2 1s. If it has 2 1s, it has to carry out. Otherwise, it has to have a 1 and a 0. So if that's the case, then we carry out. If that's not the case, then we can also look to see, did the previous stage have a carry in, and were either X or Y of the previous stage set to 1? And if that's the case, it's also going to cause a carry out, which means that we will receive a carry in. So now we don't have to wait for this previous stage to do its operation before we can tell if we have a carry in. And since we already have X1 and Y1, we can perform our operation right here immediately. And that is the design is called a carry look-ahead adder. In general, this is your equation. C1 equals this, C2 equals that, C3 equals that, so on and so forth. Okay? And when we're done building this logic, we'll have a 4-bit adder, and then we will chain 2 of them together to create an 8-bit adder. That's part of the that's the lab asks you to do that. And we're going to chain to create an 8-bit adder in a ripple carry fashion. So it'll be the same as before. Basically, you'll have a 4-bit fast adder ripple carrying into another 4-bit fast adder. So let's begin then by looking at our 4-bit fast adder. So the first thing, I'm just go ahead and I'll do this all from scratch again so we can see it. First thing, of course, that we need is a module. We'll always need a module. I'm going to call this fast adder 4 for 4 bits, which means I'm also going to have to rename this file. Great. Alright, and it's going to need some ports. And the nice thing here is that our fast adder 4, or 4-bit fast adder, whatever you want to call it, is a drop-in replacement for the 4-bit ripple carry that we've already created. So what that means is that we can come to our 4-bit adder, this is our ripple carry, and just copy this signature. And just paste it. Format it here. Oh, don't have a formatter installed. Do it later. Okay. So now we have our signature. We have a 4-bit X, a 4-bit Y, an output wire S, that's 4 bits, and a C out. The only other thing we need to add that wasn't in our original is a C in. Hold on one second. Can you guys actually see that? I realized that I left the light on. I usually turn it off and I forgot. 1 second. Is that better? Yeah. Oh yeah. Alright, sorry about that. Alright, so the only other thing we have to add that wasn't in our original 4-bit adder is a C in, and that's because we're going to chain 2 of these together. So we'll do, in our input wire, we'll do comma after Y, input wire C in. Cool. Now, just so you know, you don't actually have to put the inputs and the outputs together. It just is more legible that way. Alright. So we've got our fast adder signature. Now we need to figure out what we want to do. And what we want to do is implement these equations right here. C1, C2, C3, and C4, or you can call them C0, C1, C2, whatever you want to call them, where the last chain, the 4th one in the chain, is going to be the output of our fast adder module. And I'm going to introduce you to some syntax that's going to make this much more convenient to write. So we know that we want 4 carries, right? So let's do wire C 3 to 0 equals, oh, and then actually semicolon, and then we'll do assign C equals this. And I'll fill that in a minute. We also are going to need our G's and P's. So with this wire C3 down to 0, or sorry, it's wire 3 down to 0 C. Got that backwards. Wire 3 down to 0 C, G, and P. Okay, and we already have our S values. Cool. So now we know, based on our equations, that C1 is equal to this, C2 is equal to that, and so forth. So we can write, remembering that this is index n and then beneath it is index n-1, and above it index yeah, I'll fix that, hold on, n+1. Better? Yeah, so just keeping, basically what I'm trying to say is keep in mind that this is n+1 and n-1 if you're going to do it this way. And then let me grab those equations one more time. I'm just going to go ahead and copy these and put them in a little comment here so that I have them. So don't forget what they are. That's, I'll just grab this guy right here. Ci+1 is equal to Gi plus Pi, is equal to Gi plus Pi minus 1 plus Pi minus 1 Ci minus 1, like that. And that's our total Ci. So, or Ci+1 rather. So I'm going to begin writing by assigning my G's. So I can say that assign G equals, we know that G is X and Y, and assign P equals X or Y. If you do it that way, it will just bitwise all of those together, which is exactly what you want, so long as they're the same vector length. And then all we have to do is start putting in our equations, where this is our third equation, our fourth equation rather. So if I'm looking at my, yeah.
Don't we need to do the line instead of plus?
Yep, you're right. I do. Thank you for the heads up there. You're right. All right. So, bearing in mind that this is index 3 that I'm writing right now, this is going to be Gi, so that's G at index 3, or P at index 3, and G at index I minus 1, so that's 2, or P at index 3 and C at index I minus 1, which in this case is 2. And then you can just keep doing that for 2, 1, and 0. Once you have got all of your C's filled out, the last thing that you're going to have to do is assign something for C out, and that's as simple as just saying assign C out equals C at whatever index you want to assign it at. Does that make sense? All right. Now you're going to have to combine these into an 8-bit adder. So if I create a new file, I'm just going to show you one more little piece of syntax to help you with the combination, which is I'll do an 8-bit fast adder.v, and I'll create a module with parameters, or a module without parameters rather. And this will be my 8-bit fast adder. And it's going to also have the same syntax here as my 4-bit adder. Same signature, rather. Except that they're going to be 8 bits. So these will be 7 to 0 instead of 3 to 0. And still only one C out and still no C in. This is our top level module, so no C in, because we're not going to carry into our very top level module. And we don't need G's or P's or anything in here either, because all of that's compounded inside our 4-bit fast adder. So the big question that you're going to have to answer is, how do I connect it such that the high 4 bits go into one adder and the low 4 bits go into another if I'm getting 8 bits in? And your answer is pretty simple, actually. The syntax to do that is X and then 7 down to 4 and X 3 down to 0. Now you'll have to put those in the appropriate places and figure out how to do that. I'm not going to tell you, but that literally means the 7th to the 4th bit we're grabbing and the 3rd to the 0th bit we're grabbing. Alright? Does that make sense? Alright, and then the last thing is the test bench. Your current test bench will work fine. I recommend that you test your 4-bit fast adder before trying to combine them, so that you know that your 4-bit fast adder is working and you're not trying to figure out, is it my adder or is it my combination. So test them separately. The only thing, when you get to your 8-bit test bench, I don't want to see the full output. That's what is 128 squared? It's a lot. It's a huge table. I don't want to see it. So instead, what I do want to see is a handful of cases. So basically, you know, give me a couple of basic cases that you would expect to work. Give me a couple of cases where there's a carry out, make sure that works, and give me a couple of cases where it overflows. And you do that in test bench, and that can go in your report. Now the last thing I want to bring up is more in the way of housekeeping. It's come to my attention that the way that the labs are being taught and the way that the labs are being assigned, I don't know if I told you this already, but I'm going to repeat it if I didn't, are a week off. So basically, this Tuesday, this lab is supposed to be due, but you've barely received the information required to finish the lab and begin writing the report. And so I'm just telling everybody, just turn it in a week from your last lab. So in that case, you guys have till Wednesday, like a week from today. It'll say it's late, but I do the grading, so I'm not that worried about it. It's just that the way he's assigning them and the way that they're being taught are just off by a week.
So next week, are we working on this lab?
No, next week we'll be beginning lab 3, but you have until Wednesday of next week to turn in lab 2. Sound good? Any other questions anyone wants to ask? All right. I'm going to stop the recording then.